regions in the simplex in order to motivate the definition and characterization of the convex sets in the simplex. In the second point, we will review the Hutchinson geometry and its linear structures. In the third point, we will give the definition of convex set in the simplex, and we will characterize the basic convex sets in the simplex. In the fourth point, we will apply the definition of convexity to define the convex hull in the simplex. And finally, we will finish the seminar with the summary and conclusions. Constrained optimization is the set of theory, numerical methods, or processes used to solve problems where someone is looking to minimize an objective function with respect some constrained or limited variables. An objective function could be a cost function, an energy function, or a distance function. In linear programming and convex optimization, both theory and numerical methods are based on the concept of convexity. For example, in linear programming, the feasible region is a convex polytope resulting from the intersection of half spaces. In convex optimization, on the other hand, the objective function is a convex function, and the feasible region is a convex set. If we want to study constrained optimization in compositional data, a first step is to provide tools to define correctly what is a convex set in the simplex. We can find examples of optimization in different fields of statistics. Therefore, we wonder how we can characterize convex sets in the simplex with Hutchinson's geometry. Let's look at some examples extracted from the literature. In this paper, we have an example of optimization where the objective function is a combination of metrics and therefore a convex function. The restriction aims to be a linear constraint in the sense of Hutchinson, log ratios. So this is an example of convex optimization. I want to note that this restriction is not well defined since the ratio of positive variable cannot be equal to 0. In this example, we have a feasible region defined by the lower bounding of the variables, x1 greater than 40%, x2 greater than 20%, and x3 greater than 20%. This feasible region, as an outside observer to the simplex, if I use the standard Euclidean geometry, we may think that this feasible region is a triangle. But if we analyze this set from within the simplex, if I use the Hutchinson geometry, this set is not a convex polygon. We will see through the presentation that this feasible region is a convex set, but not a polygon. Here again, we find an example of a feasible region in the simplex defined by both upper and lower bounds of the variables. As an external observer, it might seem like a convex polygon. We will see that as a set of the simplex, this region is not a polygon, neither a convex set. One of the objectives of the presentation is to offer a result that allows us to know when a set defined by bounding the parts of the simplex is or not a convex set. Unlike the previous example, in this case, the feasible region is defined by the bound of the ratio of two variables. As in the previous example, as an outside observer of the simplex, we think that the feasible region is a convex polygon. And in this case, unlike the previous example, the feasible region is a convex polygon. More concretely, a regular hexagon in the three-part simplex. This would be an example of well-defined linear programming in the simplex. We have a linear objective function. This is a log contrast. And we have a convex polygon as a feasible region. So we have seen three examples of sets that would seem to have the same properties, but as we will see, they are totally different sets of the simplex. The aim of this seminar is to study the simplex regions with the Hutchinson geometry. Okay, let's review the basic concepts of the Hutchinson geometry. As many of you already know, compositional space is defined as the vectors with strictly positive components and the equivalence relation where two vectors are related if one is multiple of the other. This equivalence relation is known as scale invariance. The operations that provide compositional space with a vector space structure are perturbation and powering. Of all the representatives of the compositional space, the most common is the standard simplex. As you already know, the closure operator allows to select the representative from each class of equivalence of the compositional space in the standard simplex. In the vector space, we add Hutchinson's inner product to provide the simplex with a Euclidean space structure. From this inner product, we define the norm of a vector and the distance function. This whole set of elements is known as Hutchinson's geometry. Throughout the presentation, we will use the A subscript to denote that we are talking about an element compatible with Hutchinson's geometry. Let's start with the linear geometry because it is closely related to the linear programming. In this section, we want to approach to the linear combination in the simplex, the log contrast, from a geometric perspective. Therefore, we will define the objects of linear geometry with perturbation and powering operations in order to ensure that they are objects compatible with Hutchinson geometry. The first definition is the vector subspace, and we define the vector subspace generated by vectors u1, un as the set of vectors obtained by linear combinations of the vectors u1, un. Here we have two examples of vector subspaces in the three-part simplex. The normal vector to a hyperplane is closely related to the convexity and to the gradient vector of a function, as well as numerical optimization methods. So we can also define a vector subspace through its orthogonal subspace. In order to remain compatible with Hutchinson geometry, this notion of orthogonality is defined by Hutchinson's inner product. When we express the inner product in CLR coordinates, we obtain the characteristic equations of a log contrast. This means an array with total sum equal to 0 multiplied by the logarithm of the vector x. The sum of the coefficient of the log contrast coefficients are equal to 0 since they are the CLR coordinates of the normal vector. With this approach, the condition that the sum of the coefficients of the log contrast are equal to 0 is not an imposed afterward condition seeking invariance but scalar, but that it's an implicit and natural condition of the geometry of the simplex. Once the vector subspace is defined, we can define the affine subspace as the perturbation of a vector subspace. And as we have done before, we can transform this initial equation to a log contrast equation. In this example, we see in red a vector subspace and in blue the affine subspace that comes out from perturbing the vector subspace. The definition of segment in the simplex presented here is the point to understand the convexity on the simplex. As we have done previously when defining the Euclidean subspace, we now define the segment that joins 2 points as the linear combination that takes us from one point to the other, using the operations of perturbation and powering. This definition corresponds to the Euclidean definition of segment in coordinates. With this definition of segment, we are able to define convexity on the simplex. A set is convex if the segment that joins to any points of the set is contained in the set. With this definition of convexity, the green triangle, which from the outside does not look like a convex set, it is a convex set of the simplex. In fact, it is a convex polygon. While the blue band, which from the outside seems a convex set, it's not a convex set in the simplex with the Hutchinson geometry. And the way to see it is by joining 2 points with a segment that comes out of the set, as you can see on the right figure. When we work with constrained optimization, it's crucial to ensure that when we work with numerical methods in coordinates, we don't leave the feasible region and no time. As seen in the examples of the beginning of the talk, we have 2 simple ways, both algebraically and geometrically, to define constrained regions in the simplex. Algebraically simple means that it is expressed with simple equations. And geometrically simple means that the sides of the sets look like straight segments. The first option is constraining the ratio between 2 variables. And the second is constraining the limits of a variable. We again insist on the difference in perception that we have as outside or inside observers of the simplex. These two examples that we present from the outside seem to have the same geometric characteristics. However, as sets of the simplex with the Hutchinson geometry, they have different properties. So the first definition, the simple hyperplane. A simple hyperplane is generated by constraining the ratio of two variables. Its log contrast equations, as we have seen in the basic definitions, has CLR coordinates, all zeros, except 1 in the I position and -1 in the J position. Both the algebraic and the graphic representation of this hyperplane are easy to interpret. The hyperplane splits the simplex into two basic sets, one on the right and the other on the left. Both sets are affine half spaces, and in particular, it's easy to see that they are convex sets. Here we have an example where we define a parallelogram in the simplex as the intersection of four affine half spaces. To see that the red region of the simplex is a parallelogram, we can move to OLR coordinates space. We can extend the previous reasoning to any hyperplane with a log contrast equation. Given a general hyperplane, this hyperplane splits the simplex into two half spaces, the half space to the right and to the left. Both half spaces are convex sets. Therefore, we define convex polytope in the simplex as the result of intersecting half spaces. In this example, we can see three log contrasts that intersect, constructing a convex triangle in the simplex. Whenever we want to be consistent with Hutchinson's geometry, we should get used to talk about convex polytope in the simplex only in those cases where the set is the result of intersecting half spaces generated from log contrast. And only in these cases, we can have a problem of linear programming in the simplex. The second way we have to generate sets such they are algebraically and geometrically simple to interpret is by constraining the xi variable. We define the simple hypersurface as the set of the simplex that verify the equation xi equal k. This simple hypersurface splits the simplex into two regions. The upper region, defined by xi greater than k, is a convex set. But the lower region, defined by xi smaller than k, is not a convex set. The key step in demonstrating that the upper region is a convex set is the use of Holder inequality in finite dimension. In this example, we see graphically that the set x1 greater than 40%, the blue region, is a convex set, while the set x1 less than 40%, the gray region, is not a convex set. A first consequence of this result is the following example, the strip. When we constrain up and down the XA variable, we are intersecting a convex set with a non-convex set. And the lack of convexity of the strip is in the upper bound, in this case, X1 equal to 70%. We can generalize the simple hypersurface to this situation, the simplex tip. We define the simplex tip as a hypersurface defined by a homogeneous polynomial of degree 1 that cuts all the edges that converge in a same vertex. This condition, that the hypersurface cuts all the edges that converge at the same vertex, is expressed with this condition, alpha 1, alpha j negative. In this case, this hypersurface splits the simplex into two regions, the upper regions and the lower region. The upper region is a convex region. As in the previous case, the simple hypersurface, the key point of the proof is the Holder inequality. Okay, in this section, we will apply these ideas in order to define the convex hull. Given a set of points, the set of all convex combination is named the convex hull. A convex combination of points can be thought of as a mixture of the points. We can define the convex hull, as in this example, as the linear combination of the EK points. But as we will see, this definition does not lead to a convex set in the simplex. Therefore, we will see how we should define a convex hull in the simplex so that it is compatible with the Hutchinson geometry. We will define the convex hull of a set of points as the set of all its linear combination with the perturbation and powering operation, with no negative coefficient and sum equal 1. Applying this definition, we can see that the 3 points convex hull is a triangle in the simplex. So this is an Hutchinson triangle. We want to compare the convex hull defined with the perturbation and the powering with the convex hull defined with the sum and the product operations. We will see in the following examples that the Hutchinson convex hull is a polytope of the simplex, while the Euclidean convex hull has an arbitrary geometric behavior. We take an easy example. We take 3 points in the simplex and we draw the Hutchinson convex hull, that is the green region, and the Euclidean convex hull, that is the blue region. We make the graphic representation both in the simplex and in coordinates. The Hutchinson convex hull is the intersection of three affine half spaces that generates a Hutchinson triangle. We can see in coordinates, this is a triangle. But the Euclidean convex hull is the intersection of three upper simple hypersurfaces. As we have seen previously, an upper simple hypersurface is a convex set. So the Euclidean convex hull in this example is a convex set, and you can see in coordinates. So we can see both in the simplex and in coordinates that the Euclidean convex hull is larger than the Hutchinson convex hull set. Therefore, the Euclidean convex hull set is a convex set, but it does not perform the convex hull function in the simplex. It's not the minimal convex set that contains the three set of points. When we apply numerical methods to solve problems of constrained optimization on the feasible region Euclidean convex hull, maybe we are taking more points than necessary. Here we have another example. We take 3 points in a different position in the simplex, and we draw the Hutchinson convex hull, the green region, and we draw the Euclidean convex hull, the blue region. We make the graphic representation both in the simplex and in coordinates. The Hutchinson convex hull set is the intersection of three affine half spaces that generate an Hutchinson triangle. We can see here in coordinates that the green region is a triangle. But the Euclidean convex hull set is the intersection of three lower simple hypersurfaces. And as we have seen previously, the lower simple hypersurface is not a convex set. So the Euclidean convex set hull is not a convex set. And therefore, the Euclidean convex hull in this example does not perform the convex hull function in the simplex. In this case, when we apply numerical methods to solve problems of restricted optimization, if we do on the feasible region of the Euclidean convex hull, maybe we are taking less points than necessary. Let's see an easy example of linear programming and the consequence of using Hutchinson convex hull or Euclidean convex hull. First, in this example, we have a linear function, a log contrast, and the feasible region is the Hutchinson convex hull of 4 points. The feasible region is the red polygon, the red Hutchinson polygon, and the blue dashed lines are the contour lines of the objective function. If the researchers works in coordinate, it is clear that the problem is a linear programming problem. We have a linear function and a polygon as the restriction. And the researcher can use all the linear programming algorithms to find the vertex solution. In this case, the vertex solution is the vertex 36%, 28%, 36%. But in contrast, a researcher that is working with Euclidean tools on the simplex, the Euclidean function from an Euclidean point of view is not a linear function, but the feasible region, the red triangle, it is. And if the researcher is working on coordinates, the objective function is a linear function, but the region, the feasible region, is not. So this is not a linear programming problem, and the solution is not a vertex. You can see that the solution is this blue point. Furthermore, if we use the Euclidean convex hull, we are changing the type of constrained optimization problem and the numerical algorithms in coordinates. Finally, we want to apply convexity to a statistical technique. One way to identify outliers and calculate measurements of centrality in robust statistics is convex peeling. Peeling consists of removing outer layers of points so that each outer layer of points is formed by the outermost points. The way to choose whether a point is outermost is by looking at if it belongs to the convex hull. In the example, we have generated 10 random points in the three-part simplex with a normal bivariant, and we have added the arithmetic mean and the geometric mean. If we use the concept of Euclidean convex hull to create the peeling, we get this figure. This figure shows that the arithmetic means, the red point, belongs to the last layer and therefore is shown as a measure of centrality, while the geometric mean, the green point, wraps the outermost layer. This location crashes frontally with the intuition that the geometric mean is measuring centrality in the simplex. But if, on the contrary, we use the Hutchinson convex hull, we have the arithmetic mean, the red point, in the first layer, and it's an outlier candidate point, and the geometric mean, the green point, in the last layer as a measure of centrality. We can see this peeling both in the simplex and in coordinates. Finally, despite the increasingly common use of the Hutchinson geometries and OLR coordinate, the truth is that in the literature, strictly Euclidean concepts are still mixed with Hutchinson's geometry arbitrarily. This fraudulent use of strictly Euclidean tools in the simplex can lead to incorrect or contradictory results. All elements of linear programming in the simplex must be associated with log contrast, and the feasible region should be an Hutchinson polytope in order to ensure linear programming algorithms and numerical methods when we work in coordinates. We should analyze the convexity of a region following the definitions that ensure compatibility with Hutchinson's geometry. We have seen some examples of convex sets. And the basics are the half space and the simplex tip. The work that remains to be done is to expand the catalog of convex regions, and I ask you for suggestions. And to study and to characterize the convex functions in the simplex in order to progress in the study of the convex optimization. The bibliography that I have used is the papers that have been presented at the beginning, as well as the basic bibliography of the compositional data. And on the convex side, I have used the book Convex Optimization as the reference. Thank you for your attention.
Thank you very much, Jordi, for this nice presentation, and very on time. It's not 12 o'clock. We have time to discuss. And please, do you have any questions, suggestions, ideas, comments, proposals? Something for Jordi, please? Be free. Hello?
Sí.
Any questions? Comments? Ideas? Suggestions? Proposals?
Demasiada topología. La topología siempre es árida, hay que verla con detenimiento, con cuidado, ir viendo los pasos si se pueden demostrar. Es decir, no es llegar y ¡pimba!
Do you have an automatic translator for this? Because I don't understand in Spanish, please.
Pues entonces me callo.
No. And Germain, please, Germain.
Yes, well, it's I don't know if my comment belongs very much to here, but I see also Dorotea in the room, who is working, and Charlotte also, who are working on time use, and of course they try to find some sort of optimal time use combination. But there is not a known function to optimize, but the function is sort of derived from the data, with empirical data or on a dependent variable. I don't know to what extent this is related to Jordi's work or is something completely different. Sorry for being so vague.
Hello. Yes, I don't know either. It will take me some time to work through and understand what you've presented, Jordi, but it's something that we're interested in, what you're doing, and to see if we can use it in our field. So thank you very much. And really nice to see your faces.
Yeah. Okay. Any other questions, comments? Jordi, can you show, please, the slide with the examples in the beginning of the,
Yes.
the applications of these convexity tools?
those examples?
The list, the first, when you introduce, no, the previous one. Previous one. This one, okay. No. Next one.
Sorry.
This one. I think that Jeremiah is suggesting that the next talk you have to add here one point of time use studies with some application for optimization, because they are looking for the optimal combination of times to do the optimal for a function. I miss the concept of the function here. Which is the function, the objective function here, though?
At the moment, we're just using linear models, sometimes with quadratic terms, but still a linear model.
Linear model on coordinates for explaining something like a characteristic of people, no? I mean,
yeah. So we want to know the best mixture for perhaps for BMI, for body weight, or maybe for mental health, or depression, something like that.
And do you have any paper, published paper, or conference, or something like this?
But we use brute force to find the best mixture. So we just use our function to predict for every possible combination of time, maybe in 5-minute increments within a feasible area on the simplex, and then just look for the best.
Yeah. You are doing a numerical approach, you mean?
Yes, but it gets difficult with when there is high dimensions. So it's possible with lower dimensional data, but when we have 8-9 components, it's a little bit more difficult.
Yeah. Okay.
Can I ask a question regarding testing for convex? Jordi, based on your presentation, correct me if I'm wrong, but I think an important takeaway is to test for the convexity in the simplex space and not the Euclidean space. Is that correctly understood?
Sorry, repeat. Repeat the question, please.
Yeah. So am I understanding correctly if an important part here is to understand that when you have compositional data and therefore your objective function is based on log ratios, you should test for whether your objective function is convex in the simplex using the methods you presented here?
The idea is to have convex optimization. When you have convex optimization, your objective function is convex, and the feasible region is a convex region. When we started looking in the literature, we realized that many times the author mix in the definition of the region Euclidean tools in order, and then sometimes you have problems because the algorithm goes out of the feasible region and you have to turn in. So, and we want to start defining what should be a convex set in the simplex. So this is the first part, and now we should progress studying and characterizing the convex functions in the simplex. But this part is not done. We are working. Yes, have I answered the question?
Yes, you have. Yes? Thank you. Because we are doing the bad stuff right now. I think we are mixing the two, which apparently we
sometimes
isn't the right. Yeah. So what we have done right now is test for for whether our function is a convex and whether our boundaries is a convex, but using the method you just described, we should not be using. So we will definitely be keeping an eye up on.
Okay.
Yeah. Thank you.
You are welcome.
Okay, we have another question from Germain, maybe? Germain? No? Okay, then Juanjo?
Hello. Yes, I have a question or a comment in general. You are dealing essentially with convexity, that is a requirement for convex optimization, obviously. But most of the problems appear not only with the convexity of the constrained space, but the angles of this polygon where you move on. The question is, how are the angles dealt with this approach? Even if they are convex, how to prevent to use a region that being convex has very acute angles.
I haven't seen. I haven't think with this point. I don't know. Maybe Martin.
No, I don't know. Do you have any idea, Juanjo, about the angle? Angle below one degree is enough, or you need more than 5, or I don't know.
Yeah. No, it's a typical problem that appears in finite element methods for solving partial differential equations. It's a quite a standard problem. When an element gets very acute, then errors are produced everywhere. Here you have a similar problem. Even when the space where you search for the optimum is convex. So the convexity is not the only problem we have. I would start with a question about the simplex in a high dimensional situation. For instance, with the sides of the simplex, which is the maximum or the minimum angle you can get.
In order
for instance,
to
know how are they behave of how the angles are behaving. You know that in the triangle, the edges of the triangle are 60 degrees angles. When you go to the tetrahedron.
But Juanjo, in compositional data, in Hutchinson geometry, you have not 60-degree angles. You have no borders.
I don't know.
You have no borders in Hutchinson geometry. You have no angles.
But you have angles.
Maybe do you have any paper or book to read this problem with the convergence of the numerical methods in these partial equations, algorithms?
There are a lot of them.
Please send us, and we have a look. Maybe we can find there a similar problem that we have. Yeah.
I sent the books to the library.
Okay. Tell me only
so that you can.
Tell me only the title.
A shelter.
Just the title. I need just the title. Okay, thank you. We have another question from Carlos. Carlos Barceló, please.
Good morning. Thank you, Jordi, for your... Can you understand me? Yes. Thank you for your explanation. It's very clear, very interesting. Only a question on only a possibility. if we have a set of points in the simplex, I don't know if numerical is very difficult or not. It's possible to look for the convex set in the Hutchinson sense of the minimum area, including all the points. Is this in your future work to analyze this situation? I think that it will be interesting to have an algorithm or to have numerical routines to search for this minimum set of the minimum area, including all the points, and that set will be convex. Is this possible or not? Or
Well, I guess that the Hutchinson's convex hull, the idea of convex hull is this: is a convex set.
Jordi, can you present the slide, please?
Yeah.
Yes, sorry. Here, for example, if we have 3 points, the minimum convex is the convex hull. So this is the minimal is the region with less area that contains these 3 points and it's convex. And with this example, for example, if you have 4 points, the smaller convex that contains these points is the convex hull. But the convex hull in this idea to be complained with Hutchinson geometry, not with this idea that is our Euclidean idea. So the convex hull is by definition the smaller convex that contains your original set of points.
Yes, certainly. But if you have a very big set of points in the simplex, from a numerical point of view, it is possible, it is easy to search for this convex hull, or numerically is a difficult problem.
Okay, I haven't started with numerical methods. We just, by now, we just stopped on the definitions, characterization properties.
You applied peeling, no? Peeling is this idea, no? Do you have any restriction for the peeling algorithm as regards the number of points?
Sorry?
The peeling algorithms is this idea, no? You can have a data set and you apply the peeling. Do you know if there is any restriction about the sample size, the number of points?
No, I don't know.
Okay.
I don't know if this algorithm, the order of complexity, or I don't know.
Okay.
Okay, thank you.
Again, I have a comment.
Yes, please, Juanjo.
Years ago, in 2000 and few years, België, you know who is België?
Yeah.
Presented an algorithm studying the provenance problem.
Sorry,
So,
provenance.
Provenance problem. There are sources. The material, the composition of the material of the sources are mixed, and then you analyze the mixture. And now the problem is to identify the sources. The algorithm that Belge presented is based on the convex hull of the points in the simplex in the Euclidean sense. And now the question is, has any sense to do this in coordinates in the Aitchison geometry? Probably yes, I don't know. But it is a good example where the Euclidean point of view of the simplex is used in a way that is at least problematic. Perhaps reading this article, you can get some idea or alternative idea to the way Belge is dealing with.
Okay, thank you very
Okay,
much.
thank you.
You mean that this problem is known as extreme values or something like this?
End members.
N members.
N members.
N members.
But the N members are then the vertices of the polygon.
Yeah.
The polygon of the convex hull.
Okay, thank you very much.
I think welche.
Yes, Vera?
Can I? No, Juanjo, this does not work.
No.
Okay, now?
Yes.
Sorry, we are having problems with the micro and the sound.
We expect that are not familiar problems, this.
What I was saying is that if I'm not wrong, Welke developed this approach that was mentioned by Juanjo in his PhD thesis.
Okay.
Many years ago. I can, or we can check. I think he has several papers on the problem. So there must be several publications explaining the issue.
Okay, thank you. We will check. Any other question, suggestion, comment, proposal, idea? No? Then thank you very much for attending the seminar, and bye. Goodbye.
Thank you.
Bye.
Thank you.
Bye-bye.
Bye.
Bye.
Adeu.
Adeu, Carles.
Adeu. Ànim, molt bé.
Això, ànims, ànims.
I enhorabona per la paternitat, eh?
Ah, gràcies.
Records.
Gràcies,
A la
gràcies. A la Marta.
Vale. Disfruteu.
Adéu.
Adeu.